Hello, my name is Matthew Dipple with Airtight Engineering. Welcome to Module 4 of the recorded version of the Getting Real About Home Energy Efficiency workshop. This is geared towards real estate agents here in Saskatchewan. So let's get started. Module 4 is one of our core modules for the course, and it is all about energy efficiency in the home. So in it, we are going to start by going through some Canadian home energy statistics, talk about just the role that home energy use has to play in our country's overall energy use. Then we'll look at energy efficiency by end use within the home, so heating, hot water, etc. And we'll also look at particular measures for saving energy. So some particularly impactful measures and some up and coming technologies. So maybe you've heard thing or two about these things called heat pumps. We'll dive into those, take a bit of a deep dive on heat pumps for a few slides, talk about the Saskatchewan context. We'll look at HRVs in more detail, drain water heat recovery, cooling strategies, lots of things. So that you can both identify these in homes that your clients might be looking to buy or recommend them as just paths to explore for your clients. So first, looking at a Canadian context, how important is home energy efficiency? We can see here, this is a pie chart of Canada's secondary energy use, and that's the energy that's used by end users, so all of us. And in 2018, it was 9,683 petajoules, which is a huge amount of energy. 1 petajoule is the energy use of 10,000 average Canadian households for an entire year. So 9,000 petajoules is a very large amount. And we can see here that of that secondary energy use, residential energy use makes up about 12%. So it's not as big as transportation, not as big as industrial use, but it's there in third place. It's a pretty big energy user. And when we're looking at a Canadian context of reducing our emissions, of stewarding our energy wisely, residential energy use is certainly on that priority list. Interesting also to see what an impact energy efficiency in homes has had so far in Canada. So in the 20-year period or close to 20-year period between the year 2000 and the year 2019, home energy efficiency improvements saved 440 petajoules of energy over that 20-year period and about $8.5 billion of energy costs. That is a huge amount of energy savings just from efficiency. So that's, LED light bulbs, more insulation, better windows, more air tightness, better appliances, all of those things. So since 2000, residential energy use in Canada has increased by 11%, but it would have increased 43% if those energy efficiency improvements had not been made. So pretty impactful. In terms of cost that households pay, in general, the average household spends $4,500 a year on energy, and this includes about $2,100 for residential energy expenses, which accounted for 6.6% of household spending on average. Now, you might say, oh, 6.6% of household spending, not a huge amount, but let's also keep in mind that for lower income households, this would be a much larger percentage of their household spending. And also in areas where we're experiencing energy poverty in Canada. So if you've got remote northern communities where the only access they have is to electricity for heating or maybe diesel or wood even, that could be a huge burden that's easily balloons to be much larger than that $4,500 a year. So next, we could drill down into a home's energy use to ask, where is that energy going? And it turns out that the vast majority of energy in our homes goes towards space heating. So for the average home in Canada, 64% of our energy use went towards space heating. And the next in line is water heating. Turns out that water takes a lot of energy to heat up. And so 17% of residential energy use on average goes towards water heating. Next, we've got appliances at 14%, and then lighting and space cooling are there, but the smallest uses of energy at 3% and 2% respectively. So we're going to, for the next kind of half an hour, 40 minutes or so, talk through each of these different areas. So we'll start with space heating with that most impactful, the largest energy use area, and then work on down the line. So as we're talking about the different efficiency options that we can implement in a home, it's helpful to keep in mind the relative impact that each of those will have, right? So if I cut my cooling energy use in half, well, that's still only going to be 1% of my total energy use, right? Whereas if I cut my space heating energy use in half, that's a whopping 32% of my total energy use. So it is really helpful to just keep these in mind as we're going through each section. So the first thing to talk about when we talk about heating is efficient building form. Now, as a real estate agent, you're helping people buy and sell houses, and often you don't get to choose the building form, but it can be a helpful consideration to point out to your clients. So, if we have a simple building shape, it's going to have a lot less surface area that needs to be insulated and air sealed, and a lot less surface area that can lose heat and leak air, consequently, versus a complex building shape, which can actually just use a lot of energy just because of that complex shape, even if you've tried your best to insulate it well. So, just this example, we've got a picture of a passive house building on the left. Notice that the shape is quite compact and simple. It's fairly boxy, though it does have some nice overhang details on there to kind of make for some architectural interest. Versus that house on the right, look at all of the different roof pitches, uh, the the sort of jut outs and different kind of aspects to that building shape. I see some dormers, or at least one dormer there, and so those are all going to add challenge and energy use when we're trying to heat this building. And the little red drawings below, we can see a cube with a certain floor area. And all of these shapes have the same floor area. So you've got the same usable space if you're uh, inhabiting this house. Whereas we can keep going further to the right, and the more complex the building gets, the more envelope it has to be insulated for that same amount of floor area. So we could have up to like 150% more envelope that we need to insulate, and that's losing heat versus just that cube. Also interesting to note, multi-unit buildings. So if you've got an apartment or a condo, that is inherently more efficient than a single family home, just because you've got shared walls that don't need to be insulated. So final question that I would ask is, what about the size of a building versus the number of people housed? This is an interesting efficiency question for us. If I have a building that's 10 or 15,000 square feet, it's a huge mansion and it's got two people in it, versus a building that is a more modest 2,000 square feet with two people in it. That's a big difference in terms of energy use, just because of the size of building that we're talking about. So once we've looked at that sort of basic building form to understand how it might impact efficiency, we can look at a number of ways to reduce our heating energy use. And we always recommend following in line with sort of the passive house theory of the universe, which is very building science focused, to start with the envelope. So we start with making the envelope as efficient as we can, and then we move on to the mechanical system. And this has two reasons. Well, it has a number, but two that I'm going to highlight. The first is envelope improvements last much longer than mechanical system improvements. You put in a high efficiency furnace, maybe it will last you 15 to 20 years, 25 if you're super lucky. If you put in more insulation, that will last the lifetime of the building, right? That could last 70, 50, maybe 100 years, depending on how well it's detailed. So that's one reason. And another reason is improving that building envelope is going to really improve the comfort for our occupants, and also the kind of durability of that building, reduce the chance of mold growth, improve the thermal comfort. The walls are going to be warmer, the surfaces are going to feel warmer, be less drafty. So thinking back to our last module 3, when we were talking about the connection between energy efficiency and good building science. So let's start with that. And then after that, let's make sure we put in efficient mechanical equipment. So some of our options here, these 5, well, we've got 6 here. First is the efficient form, but the following 5 are kind of the core principles of the passive house design strategy. So number 2 is insulation, super insulation. Number 3 is airtight construction. 4, high performance glazing. 5, we've got thermal bridge-free details. And then 6 is heat recovery ventilation. And now with number 6, we're starting to get into that mechanical system a little bit, but it's still a more passive kind of piece of mechanical equipment. So let's break into some of these in the next few slides. Super insulation. This just means using a much higher level of insulation than is required by building codes in order to reduce our heating and cooling energy. So this might look like in Saskatchewan, R35 to 40 up to maybe R70 walls rather than the traditional R17 walls. So that's a substantial improvement in our amount of insulation. Got 2 main approaches when it comes to super insulation. One is affectionately known as stuff it, and the other is affectionately known as wrap it. So on the top, we see a couple of examples of the stuff it strategy. So there's a double stud wall on the right. It's got 2 sets of studs. We're looking at a top view. And then the space between and the stud cavities is filled with blown in cellulose insulation. So that whole cavity is just full of insulation. Some examples of wrap it on the bottom. We've got on the left, it looks like some sort of foam board insulation, and on the right, maybe a mineral wool insulation. And the structural wall is to the right, and all of the insulation is located outside of that structural wall. And then there might be some sort of screws or clips that are attaching all of that insulation back to the structural wall. So we're sort of wrapping insulation around the structural building. Next, airtightness. We talked about this in the last module, but airtightness, poor airtightness can lead to 30, I've heard even up to 40% of heating load on a drafty building. So that is quite the amount of heat loss just from air leakage. We measure air changes per hour at 50 pascals and use that as sort of a common metric for houses. And just to give you a sense, poor air tightness, I would say, is anything over 3 air changes per hour at 50 pascals. Good air tightness is maybe 1.5, and excellent air tightness is less than 1. In Canada, the average for our housing stock is around 2.5. So if you have a newer house, probably it's a little better than that. And if you have an older house, it's certainly quite likely that it's worse than that. High performance glazing. So now windows. So windows are important in particular because they're the weakest part of our building envelope. We're asking them to do a lot of things at once. We want them to be well insulated, like a wall, but we also want them to be transparent so we can see through them. And we want to be able to open them and close them. And so we're asking them to do quite a lot. And we need them to be watertight from wind-driven rain, etc. So they've got a lot of demands on them. So just to dissect briefly what a high-performance window looks like. So we can certainly have sort of a scale or range within high-performance windows, all the way from a more standard triple pane PVC window that looks fairly normal, all the way up to the picture that I'm showing on the right there, which is a Passive House certified triple pane window. So this is like, in that range of the best money can buy in terms of efficient windows. So that cutaway on the left, some of the aspects or attributes of a high performance window, it's going to have triple glazing. So in our climate, for sure, we would always recommend triple glazing. So 3 panes of glass with argon gas between them. So argon transmits less heat than air. And so that's a very important feature as well. We'll make sure that there are some low E or low emissivity coatings on that glazing. Sometimes just 1, ideally 2, at least 2 coatings. And what those coatings do is they can help reflect the heat of the sun out in the summer to reduce our heating, internal heat gains in the summer. And then they can also help reflect in the winter some of the heat that's in the room back into the room and prevent it from escaping. So they're very thin coatings of silver metal with other kind of constituents as well. So thin that you can't see them, but they help reflect heat on either side of the window. The frame is going to be insulated somehow. So we've got some sort of insulating material. The window on the right, it's actually just wood that's used to insulate, and then also all of those little air gaps in the plastic portion of the frame. And we also want to make sure that that glazing edge spacer, which is this portion right here, these little guys between the pieces of glass, those should also be insulated because that's a real weak point for windows. And finally, we want them to be airtight. So kind of standard windows often don't have the same airtightness as a well-made higher performance window. On this one right here, we can see it's got 1, 2, 3, 4 gaskets, or maybe just 3. Sorry, 1, 2, 3 gaskets. So there's 3 points of contact for it to remain airtight. Thermal bridge free details. So we want to make sure that the insulation is continuous in our house. This is the idea of if you've got a winter jacket on, no one designs and sells a crop top winter jacket where you would have your midriff showing. That's because that would be a terrible thermal bridge and you would get very cold no matter how thick and poofy that jacket is. So same thing with our buildings. We want to make sure that that insulation extends all the way around in an unbroken kind of layer around our building. So here's a picture of an area in older homes where insulation was commonly missed or was done poorly. And the picture on the right then, so this would certainly be a thermal bridge on the left here. And then the picture on the right is once that's been rectified. So we've got insulation added in there. Though I will note, there is still a thermal bridge here. So if we look right here, there's an area where I see brick, I see a metal kind of bar there supporting the brick, and then I see concrete. I don't see any insulation in this section. So this will actually create a cold spot and be a place where a fair amount of heat can escape. And the last of those passive house methods that we talked about was heat or energy recovery ventilation. So here's a picture of an energy recovery ventilator, and a good one can recover 75 to 90% of the energy in our ventilation air. ERVs, as we mentioned, module 3 can recover both moisture and heat, which is ideal in our climate, which is generally quite dry and very cold in the winter. So HRVs and ERVs are great additions. They are a necessary component of a high performance building, I would say, and are quickly becoming the norm just in general. Okay, so we've gone through all of those passive methods of saving energy. Now let's talk about our active heating system efficiency. So here's just an example for you to give you a sense of the range of efficiencies we can see in different heating system types. So an old gas furnace would have a seasonal efficiency. So that just means the efficiency on average over the whole heating season between like 55% efficient and 80% efficient. Whereas a wood stove, if you've got a very efficient wood stove, it could get up to 80%. If you have a not efficient wood stove, maybe you're like 30% or 40 or 50%. An efficient gas furnace or boiler is going to get in that 97% range. So 95 to 98.5, somewhere in there. Electric furnace or baseboards is 100% efficient. An air source heat pump, which we'll talk about more, is 200% efficient. And a ground source heat pump, so using heating from the ground, is going to be maybe 350 or 400% efficient, but for sure 300% in our climate. So this begins to give you a bit of a sense of why people are so excited about heat pumps, because all of a sudden we get to break that 100% efficiency threshold that we've been bumping up against with our other heating systems. So I'll give a caveat and I'll say that it seems like magic, but let's talk in the next couple slides a bit more about heat pumps and how we can actually get more than 100% efficient. So one caveat is we do have a bit of a difference between fuels for these. So if we go from gas to electricity, it's important to think about where that electricity is coming from when we're thinking about efficiency, sort of big picture, zooming out a little bit. So you could look at an electric baseboard and say, hey, it's 100% efficient. It's better than my gas furnace that's 97% efficient. Well, if you generate your electricity, as we do in Saskatchewan, with largely a mixture of natural gas and coal, and those generating plants are maybe 50% efficient when all is said and done, are you actually better off? Well, maybe not. You're probably better off with your gas boiler or gas furnace. That's going to change as our grid moves more and more towards renewable energy, right? We aren't going to have that same metric of, wow, I should just burn gas in my house as opposed to burning gas in the power plant. That metric is going to start to shift for sure. So let's talk about heat pumps a little bit. This is very topical, and we added in a few slides because our first session that we did of this course, we were getting lots of questions. So we thought we would just add those in and give you some of the details. So first of all, what is a heat pump? A heat pump is a device that moves heat from outside a house to inside and vice versa. It uses a fluid called a refrigerant. And so there's no air that's moving into the house or out of the house. It's actually using this fluid through some pipes between an outdoor unit and an indoor unit. We've got kind of two main types of heat pump. The first is an air source heat pump, and the second is a ground source heat pump. So my top picture on the right there is a picture of an air source heat pump. So it's got a fan in this little outdoor unit that's blowing across a coil, heating up or cooling down this liquid refrigerant, which then flows through this pipe to inside. There's another fan that's blowing across and using that to heat or cool air in the house. And then that refrigerant returns to the outdoor unit and just keeps going in that big loop. Ground source is the same thing, except our outdoor loop is underground, and it's actually just taking heat, energy, or coolness from the ground as opposed to from the air outside. I will note that an air conditioner is a heat pump. It's just a heat pump that only works in one direction. So the difference between a heat pump that can both heat and cool and an air conditioner, which can just cool, is a reversing valve. It's one valve that allows the refrigerant to move the opposite direction is basically it. And there's a few other details, some controls, a little bit more kind of process, but essentially that's the difference. So if you have an air conditioner, you basically have a heat pump. It's just a somewhat limited heat pump because it can only cool as opposed to heat. So you might be thinking, how can we get past that 100% efficiency threshold? And the reason is because a heat pump is moving heat. It's not generating heat. So the heat pump outdoor unit is taking heat from the outside air, and it's able to take heat down to very cold temperatures, which is pretty amazing. It sounds incredible, and it is quite the technological feat, but it's able to harvest heat energy from the outside, even when it's minus 20 or minus 30, and then upgrade that heat to a temperature that we would want to feel in our house, and then put that into the house. So instead of, say, a gas furnace, which we're just burning gas to generate heat from that fuel from combustion, we're actually moving heat around from outside to inside or from inside to outside. So next question we get a lot is, do heat pumps work in Saskatchewan? And the answer is yes, a resounding yes. Ground source heat pumps, to start, work in any climate, just about, unless you're in the far north with permafrost. The ground is a pretty stable temperature, and it's fairly warm. It's maybe 10 degrees, 5 to 10 degrees, depending on how deep you go, maybe like 8 feet down. So it's quite warm, and we can actually get much more heat out of the ground than we can out of the air during the winter. And so ground source heat pumps have very little trouble working here. And in terms of air source heat pumps, modern cold climate air source heat pumps that have been around for maybe the last 15 years or so, they're getting better and better all the time. And currently, many of them work down to minus 25, and some will work down to minus 30 Celsius. So, having said that, you do then need a source of backup heat here in Saskatchewan for those few days a year when it's lower than minus 30 outside. But this can be an inefficient, just electric resistance heater if we want, because it's not going to be running very often. It's just going to run, 1%, 2% of the year. And that heat pump is going to be producing the vast majority of our heat. So we can have some sort of backup heat. Could also be a natural gas furnace, right? Doesn't even have to be the most expensive, fanciest furnace. It could be just like 94, 95% efficient gas furnace, and it's just running that little bit of the year where it's super cold out. I'll also note that there's currently a lot of work going on down in the States, and the federal government here is partnering with the Department of Energy in the States on some exciting research and development to improve the number of manufacturers in North America that can produce these cold climate heat pumps and to increase their efficiency and also their functionality. So that's exciting. It's happening right now, and I think it's going to be wrapping up in the next year or so. On the right of the slide, I've got some pictures from some projects that we've worked on in Saskatchewan, just of real world examples of heat pumps here in the province. So the first, Cumberland House Cree Nation, it is a heat pump, and for the backup heat, we used a wood pellet furnace. So not a particularly efficient source of backup heat, but it's not running a huge amount of the time. The heat pump is covering a lot of that load. So that's up in Cumberland House. We've got one in Saskatoon here. This is the Radiance Co-housing project in Saskatoon on the west side, and it uses heat pumps and backup electric resistance. So these units are built pretty much to the passive house standards. They're super efficient, and so having a little bit of electric heat as a backup, even though electric is expensive as a backup heat source, they don't use very much, so it doesn't add up to be too much. And then that one on the right, Montreal Lake, this one is a greenhouse, and it's got an air source heat pump there, Mitsubishi unit, which can run down to, I think, minus 25 or 30. And it's only run for kind of the shoulder season. So they would shut it down in the coldest couple of months. So they actually don't need a backup heater. They can use that heat pump as long as they want. And then in December, January, they'll just shut the greenhouse down because not much light up there anyways. And there you have it. Another question that people have is, will an air source heat pump save money in Saskatchewan? The answer for this one is it depends. So currently, I did a little bit of analysis on this. So this isn't a published study, but just analysis that we did in-house. If you've got an inefficient or a modern efficient house, right now, it's going to cost you more to heat with a heat pump than with natural gas. And part of that is because even though a heat pump is so efficient, natural gas is like 5, maybe 5.5 or 6 times cheaper than electricity at the moment. So it's really cheap. And that's the main thing it's got going for it in terms of being a heating fuel. In this case, in this comparison anyways. So by 2030, we should see, if the carbon tax continues increasing as projected, we'll see a point at 2030 where the modern efficient house is actually less costly to run with a heat pump than to natural gas. And in all cases, we see that our modern best-in-class house, so today and also in the future, is going to be cheaper to just have a heat pump than to have natural gas for heat. So that when I talk about modern best-in-class, that's like that Radiance co-housing project. So that's sort of the passive house level of efficiency. So super efficient. And in both of those, the modern efficient and modern best-in-class houses, the reason that we're seeing savings with the heat pump is because we can get rid of the natural gas service and we don't have to pay the monthly service charge anymore. So if you're just looking at fuel prices, they come in really close, but then getting rid of the natural gas service tips the balance so that we no longer have to pay for that service charge. So there we go. There's the slightly longer answer for whether a heat pump, an air source heat pump will save money. And another question we get is, will an air source heat pump save emissions, greenhouse gas emissions? And the answer to this one is, again, it depends. So today, a heat pump will not actually reduce a home's greenhouse gas emissions if you're using grid power from SAS Power. And that's because our grid still has coal on it and it still has a lot of natural gas generation on it. By 2030, a heat pump will save roughly half of a home's heating emissions. So we're really close to that inflection point. And I've heard from some others that we're likely to hit that point in the next 3 years-ish. So maybe by 2027, we'll be hitting the point where it's actually environmentally better to run an air source heat pump than it is to run your natural gas furnace. So a couple of key takeaways. Building efficiency makes the biggest difference. Notice that cost comparison. The heat pump was making less of a difference than having a really efficient building to how much it was going to cost to heat. So that's important. Also, cost and carbon, we're reaching that inflection point with both of them. So that point in Saskatchewan where a heat pump really starts to make sense. So in the next few years. And because of that, it's important to think over the lifetime of our system when we're installing a new system in a house, instead of just thinking about, hey, what makes the most sense today? We have to recognize that that equipment's going to be installed for 15 to 25 years. So we want to say what's going to make sense 3, 5, 10 years from now as well. We didn't consider the case of using solar power, and we didn't consider the case of a geothermal heat pump, which is even more efficient. And so a lot of the sort of things that apply to an air source heat pump were already there for a geothermal heat pump. All right, so that was sort of a brief deep dive into heat pumps, a little bit of what they do, some frequently asked questions, and there's certainly lots of information out there that you can look at to understand more. And the last thing before we move on from heating is heating system controls. So you may have heard this before, but if you have a programmable thermostat or a smart thermostat, you can save energy. And the way that you do that, you don't just save energy just by having one. You have to set back your temperature by about maybe 4 degrees up to 6 degrees for an 8-hour period each day. If you do that, you can reduce your heating energy use by up to 10%. So that's pretty exciting. You don't have to set it back this much. It'll just mean less of a savings. So in my household, during the day, we have our thermostat set to 20 degrees. And then at night, we set it back to, I think, 16.5 degrees. And so that the house kind of cools off over the nighttime. We save some energy. Then in the morning, we have it set to kick back up before we wake up, barely even notice. Just a note on this, this strategy does not work well if you're heating with a heat pump or if you have a boiler. So heat pumps are designed to just provide steady, continuous, low amount of heat. And so it's going to be more challenging and you're going to save less energy if you're asking them to kind of work less overnight, but then have to do a whole bunch of work first thing in the morning to try to actually get the house back up to temperature. Okay, let's talk about water heating. So this is our next biggest use of energy in a home. So when we talk about water heating, we're talking about domestic hot water, which is not the water used to heat a home in like a boiler or hydronic system. So we're talking about the water that comes out of the tap. Got a little donut chart here of the biggest sources of hot water use. Notice that the biggest ones are the direct occupant uses rather than our appliance uses. So the shower, the bath, the faucet, those are the biggest users of hot water. And I find that kind of interesting. We can design our machines to be efficient, but it's much harder to design people to be efficient. So when it comes to hot water, it's actually really impactful our practices as individuals and our habits as consumers of hot water. A few ways to reduce hot water energy. One big one is using low flow fixtures. So if you have faucet aerators or fixtures that have a lower flow rate, even if you've got your tap turned on for 10 minutes while you wash dishes, I'm not sure who just leaves the tap running while they wash dishes, but if you do, then you're going to have a much lower flow of water through that tap and use less energy. Using Energy Star appliances, great idea, super helpful as well. And using an efficient water heater can help a lot too. We'll talk about a drain water heat recovery pipe, what that is and what it does. Insulation, so if we can insulate our hot water pipes, especially if we have a recirculation system. So we've got a bigger house and we've got piping and a little pump that recirculates hot water through the pipes to make sure there's always hot water on demand at the tap. We certainly want to have those insulated to reduce the amount of heat loss. And as I mentioned, occupant habits are so important when it comes to water use. So education and trying to motivate occupants to save water is a big one. So I've just got a few little hot water saving tips there. Taking shorter showers, waiting for a full load to run a dishwasher or washing machine, washing clothes in cold water, turning off the water while washing dishes and brushing teeth. Those are all great, easy habits to form that go a long way to reducing our hot water energy use. So looking at water heater efficiency, so similar to space heating efficiency, this UEF, uniform energy factor, you can just kind of think of it like the seasonal efficiency in that last slide, a few slides back. So 0.57 would be 57% efficient, 0.9 would roughly equate to 90% efficient, etc. So on the low end there, we've got a natural gas tank water heater. It's going to be in that 57 to 90% efficient range. A natural gas tankless water heater is going to be 80 to 96% efficient. Moving to electric tank, 90 to 95% efficient, and electric tankless, 99 to 100% efficient. And the reason tankless is more efficient is because there's no standby losses when that hot water is just sitting in the tank, slowly cooling off. I will note with tankless, it's a bigger instantaneous draw in terms of the energy or natural gas it requires. And so that is sometimes a consideration. You might not have space on the panel in your house if it wasn't initially designed with an electric tankless in mind, for example. Sometimes for natural gas, you actually have to size up your natural gas piping in your house as well. And we also have the option to use a heat pump water heater. So there are two types, two main types. The first is the hybrid heat pump. And this is the picture on the right. So it's a tank, and then there's a small heat pump sitting on the top. And it's just taking heat from the room that it's in. And so it's going to make the room that it's in colder. And we need to make sure we've got some good airflow or some heat provided to that room. And then the other type is a CO2 heat pump or just an outdoor heat pump. And so this is taking heat from outside and then using that to heat water. So a caveat on the hybrid heat pump option is that if we have an inefficient space heating systems, let's say we've got even if we have an efficient one, let's say we've got a natural gas furnace that's 97% efficient, and we've got this hybrid heat pump that's 300% efficient. Well, it's taking heat from the mechanical room, and that heat is being replaced by the furnace. So it turns out during the winter, really overall, that water heater is only 97% efficient, right? Because it's limited by the efficiency of our space heat. So it can make sense to have a heat pump in both scenarios, both to heat our space and also to heat our water. Drain water heat recovery. This is a great technology. It's super simple, no moving parts. It'll last as long as the rest of your plumbing system. It's essentially some copper pipe wound around a copper drain pipe. This is a technology that we actually did some pioneering work on in Canada, and we've got some really good local manufacturing. There's a company in Saskatchewan. Actually, I think they did just end up selling to a company out of Quebec. But this is one of the few energy efficiency technologies that we export to Europe. Go figure. So we do a lot of this in Canada, which is great. So what this does is it uses warm drain water to preheat the water that goes into our water heater so that the water heater has to work less hard. And it can also be used to preheat the water that goes directly to the shower tap as well, so that you need less hot water at the shower tap too. So one of these units, you can save 25 to 70% of the hot water from a shower. So pretty exciting. One caveat is it doesn't work for a bath because it only works when water is flowing into the hot water tank at the same time as water is flowing down the drain. So it works for a shower, doesn't work so well for a bath. But it will work with instantaneous hot water heaters too, any type of water heater. So this is a great option, and it's pretty cheap. Usually, I think it's maybe like 800 to $1,000 installed cost, and it will save that amount of money on your hot water likely in a few years, depending on how efficient your water heater is and how many people are using it. Our next area is appliances. So here's a nice figure from SAS Power. They've got a nice little tool. You can say how many people are in your household, and it'll tell you, hey, on average, this might be how much energy you're using for different appliances. So the thing that I really want to highlight is the appliances, the sort of relative energy use. So look at the kind of top 5 there. So we've got air conditioner, stove, dryer, fridge, space heaters. So if we're looking to save energy, let's focus on those top 5, or even those top, all the ones, the red bars there. So top, how many is that? 7 or so. Let's focus on those areas first. And it's not that we shouldn't make sure those other areas are efficient, but these are the most impact that we can have here. Some of our ways to reduce our appliance energy use. The first thing we can do is just doing without unneeded appliances. I find personally, because our electronic gadgets and appliances are so easy to use, sometimes I can get lazy and just use them even when I don't need to. It's just too tempting. It's the click of a button and whatever I want at my fingertips without thinking of the energy impact that that's having. We can use Energy Star appliances. So Energy Star is a great program out of the States that Canada uses as well. And it really helps push the envelope in terms of appliance efficiency. And so if you get something that's certified Energy Star, you know that it's going to be more efficient than just the average appliance that isn't certified. Something else we could do, we could use smart timers, smart plugs, or power bars. So this is something that you could do for, let's say you've got a big computer setup with speakers and all the rest. If you've got a smart power bar that's got an on-off switch, you can make sure that it's not drawing any phantom power when you aren't using it. So that's something that I use on my computer, and I try and remember to just turn off the power bar at the end of the day and then turn it back on the next morning. And again, this is really one of those user-focused areas. Appliances, it's like high touch, high interaction with our building occupants. And so all of the work that we can do to educate and motivate efficient habits in terms of gadget use is certainly helpful. I'll just highlight a couple of efficient appliance options in that sort of top 5 area. First is dryers. A cool technology is a condensing or a ventless dryer. So some of these would use technology of a heat pump. Some of them just use condensing technology similar to a dehumidifier. So they have no vent to the outside, and they don't heat in the same way anymore. You generate a bit of heat, but what they're doing is they just have a little dehumidifier inside the dryer, and it's just dehumidifying your clothes as opposed to heating them until they dry. So these can use, I've heard, maybe half the energy of sort of a standard vented electric dryer. So these are a great option. They do take a little bit longer, however. So that's something to note. If you're doing dryer load after dryer load all the time, maybe you've got 27 kids in cloth diapers, maybe it's not for you. But for many of us, a ventless dryer is a great option. Cooking is another big one. Induction stoves, so electric induction stove tops are quite efficient. And also we've got a lot of great options now for cooking with smaller appliances. So something like a microwave is a lot more efficient for heating up a small amount of food than a stove or an oven. Also, Instant Pots. At first, I was a little bit skeptical, seemed like a fad, but learning more about how efficient they are, it really, okay, their efficiency, I'm a nerd, won me over. And they're so efficient because you don't lose all the heat to steam. So if you're boiling a pot on the stove, so much heat is escaping in the form of steam. Same thing with if you're using like a crock pot, got a lot of energy loss to that steam, whereas an Instant Pot keeps all of that steam inside and uses it to cook. So it uses very little energy to cook something. Window air conditioners and portable air conditioners are generally very low efficiency. So if you find that you've got air conditioners that are just like a window shaker or portable unit that you're using all the time, I'd encourage you to move to a heat pump. Similar, you could do something similar to this guy here. This is called a mini split. So it's just got the heat pump part outside and then this little head inside. And that's going to be a way more efficient option than a window or portable unit. And just an interesting note, if you've got a deep freeze, a chest freezer is actually much more efficient than an upright freezer. And that's because every time you open an upright freezer, all of the cold air falls out onto your feet. And in a chest freezer, because of its shape, the cold air stays in when you open it. So just a fun note there for another appliance efficiency tip. Now we're getting to our second last section. So lighting coming in at 3%. Probably most of you have already jumped on the bandwagon of LED lighting, but if you haven't yet, I would highly encourage you to consider switching your light bulbs to LEDs and encouraging your clients to do the same. These are easy wins. LED bulbs are like 6 times more efficient than an incandescent bulb, and they last 10 times longer. So it's pretty tough to beat that. Yes, they're a bit more expensive, but when you look at the lifetime operating cost, they are way cheaper. They're an easy win. They pay out so fast in terms of your investment. So this is certainly one to encourage. So this little graphic is from SAS Power, and this is the savings on, what is it? I think it's 10 bulbs over a period of how many years? 15 years. And we can see that, first of all, our LEDs are saving us almost $2,000 over that course of 15 years. We don't have to replace them. They last 10 times longer than the incandescent, and they use way less energy. I have found we have gotten in my own household, we've gotten some of the like slightly fancier, like are they the G9 or something bulbs that have the 2 little prongs on the end, and they don't. One manufacturer has lasted really well. The other manufacturer has certainly not lasted 10 years, but I'm assuming that that technology is improving all the time on some of those more kind of niche or fancier bulbs. A couple other ways to reduce lighting energy. So we talked about switching to LED bulbs, turning off lights when not in use. You can get some great, just like sort of fairly inexpensive LED fixtures that are motion activated now. I have one of these in my workshop and my laundry room. I just walk into the laundry room, the light turns on, 2 minutes later, it turns off on its own. It's great. I never forget the lights on. Using localized task lighting can be a great option as well. So having a lamp in a room as opposed to turning all of the lights on in the room if we're just sitting in the corner reading. And then also sneaky bulbs. So sometimes we've got all these LEDs in our house, and then our whole yard is decked out with the old incandescent Christmas bulbs from like 20 years ago, and we're just burning through the energy, keeping those lit all year. So getting some LED Christmas lights can also be a great idea. Our last section to talk about is space cooling. So in the summer, heat enters the house through a number of ways. So the walls, the roof, and also as air leakage. We also get the sun shining in. That's going to bring heat into the house, and we're going to have our occupants generating heat as well. So whether it's the people or the pets, the appliances they're using, that's generating heat too. Traditionally, in much of Canada, we could reduce the heat entering the home and just use nighttime air to offset the need for air conditioning. We maybe didn't even need an air conditioner, but that's certainly changing with the changing climate. And if you're in a big city that doesn't have cool nighttime air, maybe it's a bit of a heat island, there's lots of concrete, you might need an air conditioner and not be able to just cool with the nighttime air. Some of our strategies for reducing our cooling energy, we can reduce the heat gain through the building envelope. We can reduce our ventilation heat gain or solar or internal heat gains. Those should look very familiar. And I even put the same picture as our heating energy reduction strategy because they're the same thing. So we can do a lot of the same things for cooling that we did with heating. I'll talk about just a couple in particular. The main one I'll talk about is reducing solar gains, but this idea of a nighttime air flush is something we can do as well. This is something that I do in my house. I don't have air conditioning. And so at night, I wait until it's cool enough outside. Then I open all my windows and I have a fan pointing out of one window in the same direction that the wind is blowing. Then I just run that fan overnight. And then the next morning, I close all the windows and turn off the fan. And usually I can drop the temperature in my house maybe 5 degrees, 3 to 5 degrees, depending on how cool it is at night, just by doing that. And it's a great way to reduce the cooling energy that I would need. And in my case, I don't have an air conditioner, so c'est la vie. And then finally, we can certainly use an efficient air conditioner. So if we're going to have an air conditioner, let's make sure it's efficient. And why not make it a heat pump? Then we get the option of doing a bit of heating with it as well. Finally, education, right? So we can also educate our occupants to adopt some energy smart habits, whether that is, that nighttime flush of cool air or other options to just reduce the cooling that we're requiring from, say, an air conditioner. So this idea of reducing solar gains or the heat that the sun brings into our house can be quite substantial depending on how many windows we have and the orientation. So here's a couple options. The first is we can use low solar heat gain windows. So windows with thicker low E coatings on the east, west, and north side, because those are the windows that are really going to bring a lot of heat in. And on our south windows, like this top picture here, we can have some sort of shades or awnings over top of the windows. And what this will do is this will allow the low winter sun, which is coming around our house at a low angle to the south in the winter. It'll allow that low winter sun in to bring in some nice heat and sunshine when we want it to, but it'll prevent that high summer sun from getting in the window. And so that's going to prevent some of that overheating from the sun. Something else that we can do too is we can use exterior blinds. This is something that's not common in North America yet, but is super common in Europe and other parts of the world. We use interior blinds here, and it turns out that having the blind inside the window does very little to stop the heat from coming into the house because the heat has really already made it inside the house by the time it hits the blind, whereas an exterior blind is going to let very little of that heat from the sun through. So this says it's letting 50% of the heat in. I've heard more like, I don't know, maybe more like 80% of the heat in. But in any case, if we can put some blinds outside, that's going to make it even better in terms of preventing solar energy from coming in. Okay, so that's the end of cooling. So just to summarize, we've got to the end of our energy efficiency for home strategies. So in summary, the main areas of energy use in our house, we've got heating, domestic hot water, appliances, lighting, and cooling. And the two big ones are heating and hot water. So if we can really focus on those to start, that's going to go a long way to reducing our energy use in our homes. And we saw as well that energy efficiency can be improved through a few different ways. So through upgrades for sure, through retrofits, through purchasing new appliances, also just through maintenance, caring for things, making sure they're working properly, and through resident habits. As we mentioned, the people inside the house have a really big impact on how much energy that house uses due to their habits. So if we can help educate people as well, that's going to go a long way to improving our home energy efficiency. Okay, great. Let's end it there, and I'll see you in module 6 or module 5.